I'll like back both. Have to go.
All right, let's get started. It's not me. Okay. Good morning, everyone. Welcome to the High Energy Density Science Seminar. I'm Federica Cupari, the chair of the HED Science Seminar Series, and I'm pleased to introduce today's speaker, Thomas White from University Nevada, Reno. Thomas White is an associate professor of physics at the University of Nevada, Reno, and is currently on sabbatical here at LLNL. He earned a master's degree in physics from the University of Bath in 2010 and a PhD from the University of Oxford in 2015, where his dissertation earned the Culham-Ted Physics Prize in Plasma Physics. Before joining UNR in 2017, he held a postdoctoral position at Imperial College London and the University of Oxford. White's research focuses on the behavior of matter under extreme conditions using high-power optical and X-ray free electron lasers to replicate environments found in planetary interiors and fusion plasmas. His work combines experiments at facilities such as the National Ignition Facility and the Linear Coherent Light Source with advanced quantum mechanical simulations. His research is supported by funding from the Department of Energy, the National Nuclear Security Administration, and the National Science Foundation. In 2021, White received the NSF Career Award and the UNR's Musel-Feltner Excellence in Research Award. He currently serves as vice chair of the High Energy Density Science Association. Today, Thomas' talk will be about high-resolution X-ray scattering, a direct temperature probe for high-energy density matter. Before we start, I want to remind everybody that this talk is being recorded. If you're not comfortable with that, you can leave the meeting. Also, this is an unclassified hybrid meeting open to external participants, so please be aware of export control issues. In-person participants, please wait until after the talk before asking questions so that I can pass the microphone to you. And online participants, you can type your questions in the chat and I will read them for you at the end. And with that, I hope you enjoy today's talk. Thomas, take it away.
Thank you very much. So today I'm going to talk about our new method of measuring temperature in high energy density plasmas using free electron lasers. I was going to start by telling you a bit about me, but you just heard everything about me there in great detail. So the main thing I'd like to highlight really now is that after going from Oxford to Imperial to Reno, I am now on sabbatical at Livermore for 3 months. I have an office down this corridor opposite Tilo. If anyone wants to talk to me, collaborate, things like that, please come and drop by my office. I'm here to boost collaborations and get to know everyone and just have a good time, really. I wanted to say a little bit about the University of Nevada, where I'm from. It's 3.5 hours from here east. So if you don't know, you can drive 3.5 hours east over the mountains and you end up in Reno, where the university is based. It's founded in 1874 and has about 20,000 students. And it's designated an R1 research institution, which is the top level of research institution. And we do a lot of research there on HED, plasma physics, laser physics, things that would interest people here. The reason I'm sort of trying to sell it, and I put this very lovely picture here of Reno with these mountains and things like that, is we're actually hiring. So before I get into the physics, I'd like everyone to know we're hiring 3 positions at the professor level. Any level, assistant, associate, and full professor. If you know anyone, we're hiring in dynamic material response, which is, how materials behave at high strain rates and things like that, pulse power, and explosives. So if anyone knows anyone who might be interested in becoming a professor in one of these 3 things, then we're doing a cluster hire in these 3 areas. Separately to that, I'm also hiring a postdoc in my group in high intensity lasers. and I'm looking for someone experimentally inclined who knows how to run high-intensity laser experiments. So if you know anyone looking for a job in that field, let me know. They can shoot me an email. Okay. Let's talk about some physics now. So this is all sort of grew out of the fact that it is hard to measure temperature in high energy density systems. I don't need to explain to everyone here like why that is, right? It's very, very difficult. And if you look at publications over the years where people have tried to measure temperature, it's normally some model dependent measurement. It could be a surface emission, SOP. It could be some X-ray diffraction measurement where we might measure the structure and use that as a proxy for temperature. But either way, we have some model-dependent technique to measure temperature. We get reasonably large error bars. And so it's sort of a well-known problem that, you know, out of the EOS variables, temperature, pressure, and density, temperature is the one that has posed a big problem for decades now. So we set out trying to find a better way to measure temperature. And what we do is conceptually extremely simple in that we take some X-rays. We'll talk about what kind of X-rays in a minute, but we send those X-rays in and we scatter them off the target in a backscattering configuration. So the X-rays go in, they scatter off the target, they come right back at us. If the atoms are stationary, then the atoms scatter back. They have the same energy that they went in with. But if the target's hot and the atoms are moving, then the atoms are, they get an increase or a decrease in energy from scattering off the moving atom, right? And we can measure that. And anyone who paid attention in school or has ever been in like a high-speed police chase, you know that I'm talking about like a Doppler shift here. So we're going to Doppler shift the X-rays off of the atoms moving in the target. So it's a really simple way of measuring the distribution of velocities, which of course is temperature inside the sample. It's tough to do. It sounds really easy, but it's tough to do. And one reason that it's extremely tough is that atoms or ions, they're big and they're heavy. We did this experiment on gold, and for gold at temperatures of a few eV, we are talking shifts of around 100 millielectron volts. So 0.1 EV shifts in X-ray energy at these temperatures. So there's extremely small shifts of energy, right? And that's just because the atoms are slow because they're heavy. But it's a very easy equation that relates the broadening that you get from the temperature. And you can look this up on Wikipedia, right? This is well known. It is used in astrophysics to measure temperatures of things in astrophysics all the time. And we're trying to do it here in a solid, in a liquid, in some HED state. And we got it to work. It does work. So, you know, the punchline here is that we're able to get this to work. If you look over here, this is a spectrum of some X-rays in our experiment. So it's about 50 or 40 millielectron volts wide. And when we scatter off a hot target, we see additional broadening from the velocity distribution of the atoms, and we know exactly what the temperature of the sample is. So it works. It's really simple. It's extremely hard to do, and I'll explain why in a second. Of course, to do this, I need a very bright source of X-rays. And because HED states don't exist for very long, right? They exist on nanoseconds or picoseconds, depending on what you're doing, I need a short pulse, a very bright short pulse of X-rays. And so typically we will go to a free electron laser, you know, the brightest source of X-rays on the planet, to do this kind of experiment. And here's a picture of LCLS, the linear coherent light source, this kilometer-long X-ray laser that's many orders of magnitude brighter than previous X-ray sources. So it's the perfect place to try to do this experiment. And to give you an idea of how bright it is, each pulse of X-rays from LCLS is 40 femtoseconds long, so pretty much instantaneous, and has about 10 to the power of 12 photons in each pulse. So 10 to the 12 photons in each pulse, which is a big number. Keep that in mind. It's also quite narrow bandwidth. So the bandwidth of LCLS is of order an EV. So if you run it in its smallest bandwidth mode, which they call seeded mode, it's about an EV bandwidth. So you maybe already see the problem that I've got a pulse of X-rays with an EV bandwidth, but the temperature broadening I'm trying to measure is 0.1 EV. I cannot do the experiment with LCLS just as it is, okay? I need to do something else to it. But it works, okay? And we're able to measure temperature inside dense plasmas. And now we have this system where we can measure temperature inside dense plasmas. There's a lot of different physics that we have been able to attack because of it. So I'm going to go through a couple of these today. I don't know how many I'll get through. The main one I'll talk about is this number 3, which is where we were able to superheat gold to temperatures many times the melt temperature. We got this into Nature this year, kind of kicked off, went a bit viral, was very fun. I did lots of interviews online. There's an AI version of an interview with me out there, by the way, where I have an Indian accent. Crazy. Yeah, don't become too famous. And then a couple of other experiments on watching the ion temperatures increase in a system after we fire a short pulse laser at it, measuring how the bonds change in something as the temperature increases. So once you've got this temperature diagnostic, this kilometer-long thermometer, there's loads of things you can do. And we're doing all of these things. Okay, but how does it work in practice, okay? So what we do is we go to LCLS, and the X-rays, they come in from this left-hand side down here. Now, the X-rays, they have this bandwidth of 1 eV, but I need much smaller bandwidth than that. So what I do is I pass the X-rays through a silicon monochromator, so to slice out a very narrow, an even narrower bandwidth of X-rays from that EV pulse. So from the EV bandwidth pulse from LCLS, I chop out the middle 30 millielectron volts. So I throw away 95% of the X-rays in order to get a narrower X-ray pulse. So I can see these very, very tiny shifts at the end of it. Then the X-rays come in and they scatter off the target. In this case, we've been using 50 nanometer gold. So very, very thin gold. And that's because we're able to heat it with a short pulse laser very uniformly. So that's why we keep it so thin. We've also done this experiment now on methane, 50 micron methane, and we've done it on thick micron size shock targets too. But we started with just very, very thin gold. It doesn't scatter much because even it's gold, so it's heavy, so it scatters a lot, but it's also ridiculously thin, so it doesn't scatter much. So if you're keeping track, we're losing a lot of X-rays when we go through this monochromator right here. We're losing some X-rays because we have very thin target. Then we have our spectrometer. And with the spectrometer, we still need to measure this extremely high resolution, right? We don't want to ruin it. And so the spectrometer, the X-ray spectrometer, is a very special spectrometer. Normally, you would take a crystal, you would bend it into the shape that you want, and that would be your spectrometer. But if you bend a crystal, you introduce strain in the lattice, and that can reduce the resolution of your spectrometer too much, and you won't be able to see the small shifts we're looking for. So we use these diced crystal analyzers, which is just a way of saying that it's made up of hundreds or thousands of flat single crystals that are positioned in the right location. So they're extremely expensive, but they don't reduce the resolution of the spectrometer. So they keep a very high resolution in the spectrometer. They sit here a meter away from the target. And so you can see that the solid angle they cover is, they're about 10 centimeters wide, a meter away. So you see that they cover some small solid angle. So we're losing some photons there too, okay? And at the end of the day, we have they scatter or diffract onto a detector here, and that's our spectrometer. So as the X-ray energy changes, because the atoms are moving, the position where the X-rays land, it changes on the camera. It's just Bragg's law, right, to do that. And then we get this broadened spectrum from this hot sample. Once you put all of this together, right, LCLS has 10 to the 12 photons at the start. We measure 1 photon on the detector, just 1. So you can imagine we throw 10 to the 12 photons at something, one comes back, and I go, okay, now I know the velocity of one atom. That's not temperature, right? So we have to do it again and again and again at high rep rate, each time measuring the velocity essentially of one of the atoms inside the sample, and we build up a distribution. And so to do that, we have the sample on a sort of fast stage where we can repeat the experiment at. This was done at 1 Hertz, but we are now able to go at 10 Hertz. So then you are collecting 1 photon every second or 10 photons a second to build up the spectrum. And you can see the spectrum on the right here. I think it's made up of maybe 1,000 photons or something like that to be able to, you know, fit a width to it appreciably. And in this one, we heated it with a TISAF laser, just a millijoule of energy, just to pump the system and see what we would see. Because there's X-rays coming in and hitting the target, for free, you might as well put an X-ray diffraction area diagnostic in there and get the X-ray diffraction at the same time, because you get that for free because you are X-raying, like sending X-rays towards your target. So here you see the diffraction lines of gold, and then as it melts, as it heats up in the picoseconds after the laser pumps the system, you see the diffraction lines sort of vanish. And here's a video, a live video of us shooting the gold grid. So each second, right, we pump it, and then we delay, the X-rays come at some delay later to measure the temperature of whatever that system got to. If you ask me what is the biggest challenge with this technique right now, I would say the thing that is holding us back is financial. Each of these target frames costs many thousands of dollars, such that each target here, each square, costs about $1. So we're sort of paying $1 per photon in this technique. And you can imagine when we're running at 10 Hertz, I'm just seeing the dollars evaporate as we're doing this experiment. So it's, maybe if anyone wants to throw me some money, right? Yeah, so the limit is financial, yeah. The spot size of the optical laser is 300 microns, about the size of one of these grids. The spot size of the free electron laser is a few microns. So the free electron, we're probing the middle portion of the larger optical spot in this particular experiment. Okay, so that's how it works. What did we do with it? Well, the first thing we did, so we have this setup, right? X-rays come in, we monochromate them to get the very narrow bandwidth. We look at the spectrum that scatters off them. We pump it with a short pulse laser. And overall, we get about a 50 millielectron volt resolution of the entire setup, which takes into account the incoming bandwidth and then the resolution of the spectrometer. And that's around 10 to the minus 6 resolving power of the spectrometer, which is crazy good for X-rays. Okay, what does the short pulse laser do when we fire it at a thin piece of metal? Well, it initiates an energy cascade. So the short pulse laser comes in, it excites some electrons in the sample. Now, I know everyone in this room loves high intensity lasers, and you're thinking, oh, fast electrons, like capital MEV electrons that stream through. But we are using a millijoule of energy, so a tiny amount of energy in a 300 micron spot, so it's extremely low intensity. And what we're really doing here is exciting ballistic electrons, which can go up into the conduction band and stream through the 50 nanometers of gold. So it's much weaker than you might naturally be thinking of. Those electrons stream through, they collide with the other electrons, the thermal electrons, and heat them up. And essentially, within a picosecond, you get a system where you have hot electrons, the ions are still quite cold, and then they come together and equilibrate in the next 10 picoseconds. So the energy flows from the laser into the ballistic electrons, into the thermal electrons, and then eventually into the ions in the system. The question is the gold optically transparent? The gold is not optically transparent. So we are using 400 nanometer light, frequency doubled light from the TISAF laser. The skin depth is a few nanometers. The sample is 50 nanometers. So we are relying on the ballistic electron transport to uniformly heat that sample. Okay.
The A naught of the laser that you're using, or roughly what energy electrons are you making?
The energy I couldn't tell you the A naught, it's real low, but it's the energy of the electrons it's just a few eV. It is just promoted into the conduction band. The sample gets real hot still. It's so I spent a lot of time doing warm dense matter studies, big lasers. I realized here, if you have a 50 nanometer sample, you can heat it up to electron volt temperatures with a millijoule of energy. You don't need a crazy amount of energy if you have a very thin sample. Now, there are downsides to having very thin samples. They don't last very long, for example, but you can still reach solid density EV conditions very easily. And so here is sort of some of the results. So here you see this crosses is the temperature of the ions versus time. So we fire the laser here, and then the ions heat up, heat up, heat up, heat up, heat up. And then eventually it flattens off, right? And that's when the ions have stopped giving the electrons have stopped giving their energy to the ions. So the measurements of these points right here. So the measurements of these points right here. And then in red is what you would imagine the electrons to be doing. So if you were to take the heat capacities of the electrons and ions, you can sort of solve this system to guess or sort of model what the electrons would be doing to see the time scale over which these two things come together. And we were able to turn the laser up in intensity. So we have to do this for 4 different laser intensities. So here you see the laser intensities are the lowest, and then we can double it, and we double it, and then even higher here. And you see in each case, the system heats up. We strongly see the increase in temperature in the ions over time in these experiments. Because we have the X-ray diffraction diagnostic sort of as a ride-along for free, we can easily say, oh, when is this sample going to melt? When does this sample melt? Because we see the disappearance of the diffraction lines. And so we can add a vertical line to each of these that says when the sample melts. So now we know the temperature versus time of the ions, and we know when the sample melts. There's an elephant in the room here, which people might say there's a jump. You notice there's a jump in all of these. Well, certainly in the high intensity ones, there is a jump in the ion temperature upon melt. We don't know what that is. I will admit that we do not know what that is. We have 3 possible explanations for what it is. One, the sample expands rapidly as soon as it melts, and we would confuse that for temperature in our diagnostic because we're measuring the velocity distribution. So that could be a massive expansion upon melt. The other thing is sort of a negative latent heat type thing where the heat capacity of the solid and the liquid are different, and that does genuinely create a jump in temperature upon melt in a superheated system. So if you superheat far beyond melt. And the other one is that there genuinely is a jump in the electron-ion equilibration rate upon melt. Could be that too. So we're not able to distinguish between those in this particular experiment. And so we've really focused on only the pre-melting solid portion of this experiment because we do not understand exactly what's going on after melt yet. And we have ideas on what we would like to do. We'd like to add a Fourier domain interferometer on here to measure the expansion in the situ and things like that. But the first thing we want, yes. The first thing that we wanted to do was we wanted to write a paper that said, oh, we can measure temperature in HED systems. That was what we wanted to write because it's never been done before. And we essentially put all our eggs in the one basket of this one point right here, okay? And if you look at this point, this is a measurement of the ion temperature. And if you go across, you'll see it's about 20,000 Kelvin. So it's 2 eV, 20,000 Kelvin. But this is still in a solid. So there's diffraction lines still. So this is a 20,000 Kelvin solid. And we looked at that and thought, that seems pretty hot for a piece of gold. The melt temperature of gold is 1,300 Kelvin. So we're many, many, many times the melt temperature. And we thought, could we write a paper on that? Is that interesting? So I Googled, you know, how hot can a solid be? Did this about a year and a half ago. And there's a lot of work out there on this phenomena of superheating. So heating something up beyond the phase transition, but it not going through the phase transition, okay? And I hope this plays because this is a cool video. You know, the most famous superheating sort of experiment you can do at home is, yes, you can put a glass of, you should never microwave water, right? And the reason is because if you can heat it beyond the melt temperature, I'm going to be quiet while this happens because it's, oh yeah, look at that. We'll watch it again, don't worry. You can heat something beyond the phase transition, and you can heat water beyond the phase transition, so it's above the boiling point, but it doesn't boil because there's a smoothness of the glass. There's nowhere for that nucleation front to nucleate. And, okay, one more time. And as soon as there's any shock to the system, so this guy drops in like this penny, then suddenly it all boils at once and it explodes. And people get burnt every year in America because of this. So this is my like public service announcement. So that's superheating, going beyond the phase transition. The same thing is happening in our gold in that we heat it up beyond the melt temperature, but it does not melt, right? And there is a lot of work on how far you can superheat something, okay? And so I'll give you a history of superheating because it's kind of fun. It started way back in 1948. This guy, Walter Kaufmann, he actually predicted a supercooling limit. He said, how much can I cool something down and it stay a liquid, so not freeze? And what he did was he took essentially the entropy of a liquid and the entropy of a solid, and he just went like this and extrapolated them down. And there was a point where they crossed. And he said, well, if you keep going, I'm going to get a solid with a higher entropy than a liquid. And that's weird. That can't exist. And he said that if that happens, you will get a spontaneous freezing into a glass transition, essentially. And he called this the Kaufmann temperature. I don't know if he named it after himself, but that is what it's called. It's called the Kaufmann temperature. You cannot cool it down. And a lot of people have tried. So 3,600 citations to this paper as people try to approach this limit and go beyond it and then fail. And no one has ever got there. But, you know, it's a fun thing to think about. 30 years later, these two other scientists, Fecht and Johnson, wrote this paper where they just did the same thing but upwards. I don't know why it took 30 years for someone to say, oh, let's just go upwards in temperature. But they did the same thing. They just took these entropy curves and they went upwards, and they crossed at 3 times the melt temperature. So they said that you can never, ever heat something up beyond 3 times the melt temperature. That is the ultimate limit of superheating, 3 times the melt temperature. And it's harder to try, so only 300 citations, so 1/10 of the number of citations, because it's much harder to rapidly heat something up and see how hot you can make it than it is to cool it down. In addition, there are lots of other things that cause essentially melting to happen before you can even try to get to the ultimate limit at 3. There's lots of other limits at like 1.25 and 1.3 times the melt temperature. And I'll say one of the reasons I think this work got so widely recognized is because each of the ways in which they can melt are called a different catastrophe. So you have the entropy catastrophe, the rigidity catastrophe, the homogeneous nucleation catastrophe, and together they're called the hierarchy of catastrophes. And that's a sexy name for anything in science, right? And so the question is, like, what is the ultimate limit of superheating? 3 times the melt temperature is what people thought, but of course, as I just told you, right, we got to 14 times the melt temperature. Yeah, I don't need to show that, but we got to 14 times the melt temperature in our experiment. I do wonder if this might be the hottest solid ever recorded on the planet. I didn't write that in the paper. I'm too scared to write that in the paper, but I will suggest it might be to people. But we managed to publish this paper, right, on this superheating. And you might say to me, if the ultimate limit of superheating is based on this entropy crossing, did I create a system where the solid has higher entropy than the liquid? And the answer is no. That I think I would be, that would be weird to suggest that, although there are some things that can happen in. What we said was that if you calculate the entropy crossing, so here's the entropy of a liquid, and here in the light blue is the entropy of the solid, and they cross at 3 times the melt temperature for gold. But if you heat something up rapidly such that it cannot expand, then the entropy of the solid becomes this dark blue line, and the lines no longer cross. So that was our explanation for this in the paper. And so I think it's an open question yet again, how hot can you make something before it melts? I don't know, but I would argue that it's at least 14 times the melt temperature, which is what we saw in this experiment. Okay, so that was our fun paper where we were showing, oh, let's see what we can do with this. And it was all based on that one data point, right? Someone told me once, the more data points you have, the lower the impact the journal you get in. So we focused on one first, and then we're going to do the real science now. So next, the main reason we did this experiment was to look at the phenomena of electron-ion equilibration. So we wanted to ask ourselves, if we dump a load of energy into the electrons of the system, how fast do the ions heat up? So that was the reason we did the experiment in the first place, to look at this sort of cascade of energy down through the system that I mentioned earlier, and to measure this time scale properly, like how fast do the electrons and ions equilibrate. Why is it an interesting problem? Yeah, we'll skip that one. Why is it an interesting problem? Because if you look here, so this is the electron-ion coupling parameter. So it describes how fast the two systems come together. You will see that there is a wide variety of results from the theorists on this front. So there is an order of magnitude difference in all of these different models for electron-ion equilibration. So it's a good place to go and try and measure this if you can. And since nobody has been able to measure temperature before now, then it seems something that we should be able to do with our diagnostic. In addition, we make our sample really, really, really hot. So I know it was only a millijoule of energy, and it's getting to a few eV, but the electrons are getting much hotter than that. So if I go back, well, the electrons are getting much hotter than that. The electrons are getting to like 8 eV. So on this graph from these theorists, our system is sort of way over there in the wall, right? And so there's not even many models that go out there. Some of these go a bit further. So that's what we wanted to do. It's pretty easy because we already had all of this data, right? So we have these ion temperature distributions, and what we do is we just fit them with a 2-temperature model. And in each of these cases, we are able to find the electron-ion equilibration rate, how fast they're coming together, essentially the slope of this line right here. We did some clever stuff with a Bayesian error analysis. That's why this looks all fuzzy, because we did a Bayesian error analysis on this in order to extract the slope of each of these lines in the 4 different cases that you see here. And the results were kind of interesting. So on the right, you see our experimental results here for this particular one. So you see our electron-ion coupling rates versus electron temperature. Why is this interesting? First of all, I hate this point, right? Because it goes through every single one of the models except this one. So that's pretty annoying. And that's because the slope is quite shallow there in the electron-ion equilibration. So there's a lot of error that can be fit to it. And people keep saying to me, why are your error bars so big? Why are error bars so big? And the answer is because I'm honest. And these people are not, okay? That's what I'm going to tell you. They don't even have, these are experimental papers, by the way. So like the main conclusion is that we strongly disagree with these experimental papers that are down here. And I have some theories on why they got that wrong. But the error bars are what the error bars are. I mean, that is what they are. If you imagine trying to fit like the slope to these, there is plus minus 50% that you can get from that. It's just the way it is. Why do the error bars on each point here come from? that is essentially from the Poisson distribution of photons. So if we had more photons, these error bars would be smaller, but because there's a few photons in that distribution, then that's where the error bars of each of these individual ones come from. And now we're running at 10 hertz. Like I said, we could shrink these error bars if I had more cache. But we're trying to get this published right now. We just submitted this to Nature Comms, and it's under review. And the main point is we disagree with the previous experiments, not really sure about the theories, but we sort of see quite a flat equilibration rate, as if, if you pump something hard enough, the rate of electron-ion equilibration is sort of cut off. Like there's a maximum at which energy can flow between the two, and we sort of see that with this experimental data right here. Okay, I'm going to tell you about one more physics thing which we did, which is measuring the bond strength and the Debye temperature in samples. So people might not know too much here about bond strength, Debye temperature, but there is this thing called bond hardening. So if I heat up the electrons in the system, but keep the ions cold, so I have a very non-equilibrium system, hot electrons, cold ions, the bonds get stronger in metals. At least this is the prevailing theory. The bonds get stronger. So the atoms get, they pull together. In a semiconductor, the bonds get weaker. This is called bond softening. That leads to phenomena like non-thermal melting. You might have heard of this. And so there have been predictions for a long time. Starting by Vanina Recalls in 2006, she wrote this paper where she said, here is the bond strength, which we sort of parameterize by the Debye temperature. So the hotter the Debye temperature, the stronger the bonds. And she said, as the electron temperature goes up, the bond strength goes up. So it's kind of counterintuitive. You take a material, you whack a laser into it, the electrons get really hot, and the material gets stronger for a brief amount of time, right? So there is an inverse relationship, so don't look too carefully about this massive equation, but there's like mean square displacement of the atoms, how far they're vibrating around is inversely proportional to the Debye temperature. So as I make the Debye temperature go up, the atoms get more strongly bound. So that is what we're seeing here. It's interesting because even though everything I just explained to you is sort of generally believed to be true, there is this sort of Goldilocks problem of bond strength, where over the last decade or so, there have been some papers where they say bond hardening, some papers where they say bond softening, and some papers where they say no change whatsoever. The interesting thing about all of these papers, from my point of view, is they actually all have extremely similar experimental results. So if you look at their data, it's basically the same in every single one, right? And what they measure diffraction lines from gold that they pump with a laser, and they all essentially measure the same thing. So why do they all have different results? It's because they all had different guesses for what the ion temperature was, which they're not able to measure. So they all have different models for what the ion temperature is. So they assume different amounts of energy go into the sample. These guys put a factor of half in and just say, oh, half the laser energy goes in compared to these people. I don't know, right? So because everyone's guessing the ion temperature, they're all able to come to different conclusions with essentially the same experimental data set. So what we have, though, is we can do the same experiment. So we've got this massive equation I showed earlier. And essentially, if you measure the ion temperature and the diffraction peaks, you can pull out the Debye temperature. For those of you in the know, this is like Debye-Waller theory. This says the diffraction peaks strength is related to the vibration of the atoms. So if the atoms vibrate more around the lattice sites, the diffraction peaks go down. If they're strongly in the lattice sites, the diffraction peak intensity will go up. And if you combine that with a measurement of the ion temperature, which you see here, then you can directly measure the Debye temperature with no approximations whatsoever. So I know exactly how strong my bonds are. And I'll sort of skip ahead and say that we did this. So we measured the Debye temperature in these systems for 4 different electron temperatures, and we got these points right here. So these are the points we got. This is the prediction of the bond strength from the original paper. And you can imagine when I saw this, I said to my graduate student, Travis, like, you've made a mistake. Like, you've made about an 80 Kelvin mistake somewhere. Go and find it. Like, this is clearly meant to be up here, right? And we could not find a mistake in anything that we did. We're like, there's no free parameters. Like, you just plug it in the equation, the ion temperature and the Bragg peak intensity, and then out pops this. There was nowhere to go. So we spent a long time thinking about this, and eventually we decided it's because our system is already quite weak at room temperature, because this prediction here is for single crystal gold, so bulk single crystal gold. But we had polycrystalline gold with extremely tiny grain sizes. So grain size of the order of nanometers, I think. And so what that means is that our system already is weak to begin with. And so we can look up the Debye temperature for extremely polycrystalline gold, which is what we have, and it goes right here. And so this is our suggestion of this is the starting point for our measurement. And then we see bond strength increases afterwards. And maybe this is another reason that people have argued over this for years, because if you were to just do this experiment here, you would say, oh, this has dropped compared to room temperature gold. But actually, it's gone up compared to polycrystalline room temperature gold. And I did get permission from Vanina Recalls to be able to do this to her theory and just shift it down onto my experimental results like this and show that we do get the trend right, or she got the trend right, and we all agree. We just might be looking at slightly different systems. Okay, that's the end of my talk. There's a lot of things that we've been able to do with our new temperature measurements. Here we are on the experiments. I think one of these was taken at 5 a.m. and the other at like 5 p.m. Thank you to everyone here, especially thanks to Bob Nagler at Slack, who is sort of my partner in crime on a lot of these experiments. I will just finish by saying, so this did like pop off, like went viral, and we were in lots of really cool newspapers or magazines. This one, I think, makes me sound like an idiot. Despite working really hard on this, it was an accident. Okay, fine. But I will say that these people were not as mean as all the people on Reddit who had a lot to say about what we did. And I will leave that up there for everyone to look at while I take questions.
Thank you. That was a very interesting talk.
Thank you. This might be reviewer 2.
All right, we have a few questions around the room. And again, folks online, feel free to write your questions in the chat.
Great talk. So the question I had was...
Is that on?
I don't think so. Tried to turn it on.
Oh, it's on? Okay. Oh, okay.
The question I had was, the bonds harden, so how do you know that the melting temperature is the same? Shouldn't it change?
No, it does change. It does change. So we are currently writing the bond hardening paper, and in that, recalculating the superheating result based on that. Now, it actually doesn't matter because the bond hardening paper is sort of like about here. So the Debye temperature is actually not that different to single crystal Debye temperature, right? But just seeing where we end up on here. So it changes the superheating result from maybe 14 times to like 12 times the melt temperature. So it doesn't make a difference. But I will say that I was worried when I did this. I was like, oh my gosh, is the Nature paper completely wrong? But it's okay.
Thanks.
So how are you specifying the solid-liquid transition in those other plots if it's superheated?
We just wait for the Bragg peaks to disappear. So, it's a video, right? Yeah. Like we just watch these Bragg peaks, solid, 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 and then at some point they disappear, and then they say that that's the liquid.
Okay. And then could you just go through the what was the the reasoning for why you can get to such a so highly superheated in this specific experiment?
Yeah, so well, a lot of the melting catastrophes at the lower temperatures, like these ones right here, are time-based. They require some time to happen. Like homogeneous nucleation, you need to be able to nucleate voids in the sample in order to be able to melt. That takes some time. And so if you do something really quickly, you can very easily bypass all of these right here. In theory, the 3 times the melt temperature should not have been able to be bypassed. You should have hit it and not been able to go past that. But we say in our paper that if you recalculate the entropy lines and you don't allow the target to expand, then the 2 lines never cross. And so instead of suggesting that we broken the entropy catastrophe, which we did not do, instead what we did was we would move the entropy catastrophe point up in temperature somewhere else. It's an interesting question of whether these 2 lines do cross again. And actually, the solid entropy, the dark blue, if you heat something up really rapidly and you get rid of all the time effects, the solid entropy essentially becomes just 3R, the gas constant, or 3 kBT, depending on your favorite units. It's sort of given by fundamentals. But the liquid entropy, this is probably not correct for the liquid entropy. There's a great theory of what the entropy of a gas does at high temperature and the entropy of a solid. They become essentially the number of degrees of freedom over 2 times R. So the solid has 6 degrees of freedom and the gas has 3. So you know what they are in this limit. But the liquid is sort of a mess, and it's sort of a well-known problem of like what is the entropy or the heat capacity of a liquid and how does it change as you go through these temperatures. And so whether these 2 lines cross at all, I think depends on the functional form of the liquid entropy or the liquid heat capacity across the temperature range. And that's not known. Yeah, I don't think it's universal for sure.
We have a question online from Alfredo Correa Tedesco. One of the properties of superheating is that it is reversible. If you superheat without reaching spontaneous transition and then cool down, nothing should happen. In your experiment, is it possible that the temperature that you measure is not really an equilibrium temperature, but simply some characteristic velocity of at that point, inevitable, irreversible, Coulomb-like explosion?
It's possible. It's absolutely possible that we're just measuring. It is not reversible, right? And one of the problems is that it rapidly expands at this late time. I can't answer that experimentally because you cannot stop, right? Our heating process is the electrons. The electrons are dumping energy into the ions. So already it's slightly different from equilibrium thermodynamics there in that we have a non-equilibrium system with the hot electrons and cold ions. And you cannot turn off the heating of the electrons just before the superheated state. We cannot say, okay, now the electrons are going to stop dumping their energy into the ions just before it melts. So experimentally, there's no way to do that. So it's a good question, and I don't know.
So you had this interesting jump when you transitioned from solid to liquid.
Yep.
Did you try to analyze the liquid for its density? Did you analyze the diffraction?
We were not able to see the liquid diffraction very well on this experiment, and it has been a source of contention. And we saw it a bit here in this low one, but not in the higher ones. And our best guess is that we superheated so much that when it became a liquid, or melted, it was already really hot. And that gave a very broad liquid diffraction peak straight off the bat. So instead of seeing a nice liquid diffraction peak that you could fit and get the density from, so we just saw a very broad background come up that was sort of useless on that front.
And did you see any thermal diffuse scatter in the solid?
Yes, we saw thermal diffuse scatter in the solid. We're currently playing at fitting the thermal diffuse scatter because a paper that Justin came out with recently was saying that that's what you should do instead of the Bragg peaks. Yeah.
Yes. So you did this experiment on gold, which has a rather low melting temperature.
Yep.
What about doing it on tungsten or?
So we
something
have
else?
done it on a variety of metals now. We have done it on gold, silver, copper, tantalum. The issue we have, so there's a couple of issues. One is that we're already at 1 photon per shot. So the scattering goes roughly as z squared. So if you go down the periodic table, the experiment becomes much more complicated and necessarily more expensive to do. And so it is a challenge. The other thing is making these 50 nanometer targets. So we buy all of our targets from this company, Luxor, who do a great job, but extremely expensive. But nobody else that I have spoke to has been able to make these. And the metals they can make and the metals they can't make, to an outsider like me, are completely random. They're like, this material plays well, we can make silver. We asked for tungsten, and they said they cannot get tungsten to work. So it doesn't, I don't know how they make it. They grow it epitaxially, and then they like float it onto the grid. It's quite a complicated procedure. And it sounds more like an art form than a science when they talk about which metals work and which ones don't. Yeah. But we now have got this experiment to work on thicker targets. So we have done, we've done some, we did a run on, oh yeah, we did a run on, so we had 10 micron iron with an ablator in front of it. So a standard shock, 50 micron of plastic, 10 micron of iron. We shock the system, send the shock through. The shock goes into the iron, and then we measure the temperature at the breakout point. So we can measure the temperature of the shock state right here. And it works pretty well. So what you get there, a thicker target means more photons scattered. So there we have more flexibility with the materials that we can use, and that's why we're able to use iron. And we were getting hundreds of photons per shot, so it was really good. But the long pulse laser at MEC can only fire once every 7 minutes. So, you know, there's pros and cons of that. But what you get when you do that is not just the temperature from the broadening, but you also measure the particle velocity of your shock, because you see a shift of the spectrum, because it's all moving with one velocity, and then you see the broadening. And so here's the prediction, right? Here's the cold, and then here's the broadened shifted spectrum. And in the experiment, we measured this broadened shifted spectrum pretty well. So we were able to measure the particle velocity and the temperature behind the shock. We are having some trouble mashing this up with the visor right now, and we're talking to some people here to try and figure that out. But with the thicker shock targets, yeah, you have a lot much more freedom in terms of material choice.
We have a comment online from Azat, and then I'll pass it around in the room. Thank you for the great talk. I would like to note that one of the earliest detailed experimental studies of superheating was performed by Taman and published in 1910. Also, recent work by Schmelzer and co-workers provides a modern discussion of the Kaufman paradox and proposed routes towards its resolution, including theory and simulation-informed analysis. Thank you.
That's interesting. I didn't go back far enough. You would think 1948 would get you there, but no.
Was there a question?
John, I have one. I have one.
Right here. Okay, and then you can pass it.
Yeah, so I mean, essentially you're saying that it becomes a liquid when you stop seeing the diffraction, solid diffraction, which kind of makes sense. But I'm wondering, you know, the time when you lose the periodicity of the solid lattice has to be related to the diffusion time of the atoms. And so it feels like there's a connection between the amount of time it takes an atom to diffuse a lattice constant or something and the time that you would actually see the diffraction disappear. And so I'm wondering, either there's maybe a way for you to take from your data to measure the diffusivity of the atomic diffusion in the gold, or to try to estimate how long it takes the diffraction lines to disappear if you really have, you know, that kinetic energy in the material.
yeah, I think we could, I mean, you could do that. I mean, that's kind of what we're doing with the bond strength measurements in a way.
It's
It's
kind
not
of, but I'm
exclusivity.
wondering, is it possible that it's 4 nanoseconds when you put in 2 EV or whatever you're measuring, that it takes that long for the lattice to
So
lose periodicity?
we predict, I mean, we looked at how long it would take something to melt, because I mean, the argument that all of this is totally boring and useless, I mean, of course, the temperature measurement in HED is cool, but the argument that the superheating thing is not that interesting is that if I take something and I dump in X amount of energy, an infinite amount of energy, but I wait 0 time, then that's not an interesting thing to say, right? That's just saying I didn't wait long enough for it to melt. That's not an interesting measurement. The interesting thing is to say I give it enough time to melt, but it doesn't melt. And so we spent a lot of time in the paper trying to argue that it has 2 picoseconds is plenty of time for it to melt at these conditions. Do I have it? So there are plenty of predictions of melting time versus superheating that you can look up, but essentially it should melt within a couple of phonon periods if it wants to. I don't want to give it too much like sentience, but yeah. So it should melt if you superheat it, you know, to 14 times the melt temperature on a very short time scale, according to the prediction. So I'm arguing that it's not just that we heat it really quickly and don't wait long enough. On the diffusion thing, I'd have to have a think about it.
Yeah. I mean, is it possible to try to do an MD simulation of something like this to see a movie of?
We've trying to do MD simulations. The problem with the MD simulation is this bond hardening effect. So if you want to do a classical MD simulation, the question becomes which potential do you use? And if you have a system where the bond strength changes in time as a function of electron temperature, that becomes a very hard classical MD simulation to do. So then you do quantum MD, maybe you can do quantum MD, but that in this beyond my abilities to do at that point, yeah.
Okay, very nice talk, Tom. One thing I missed was when you compare the inertial confinement time of your target to the equilibration time between electrons and ions, how do these 2 times compare?
Well, so yeah, inertial confinement. So the expansion of the target after we hit it basically is a very important question. So we see no evidence of expansion at all in the solid phase. And why can I say that? Because if we look at the Bragg peak location versus time, which of course is related to the lattice spacing, the Bragg peaks do not shift in any way. So we see no appreciable expansion of the solid up until the melt point. And this is kind of odd to us, but it is what we saw. And it matches 2 other papers. So these are people who have shot similar gold foils with similar laser intensities. And they did FDI, so Fourier domain interferometry of the surface, to look for expansion. And they also see no expansion up until melt, and then a sort of expansion after melt. And so this is why we have concentrated on the pre-melt stuff in all of our papers, because we don't really know what's happening after melt. And I cannot tell you the arguments that we have had amongst ourselves about why is this solid, which is at EV temperatures, not expanding. It doesn't seem to expand. It could be the bond strength thing, that we simultaneously increase the bond strength as we heat it up. I don't know. Yeah.
Again, that would be a fun MD simulation.
But you got to have the electrons
I'm
and
not gonna do
ions in there, and then this becomes almost intractable.
Maybe a comment. To the extant code, you were showing some results on it. I mean, this might be capturing this bond hardening. It's like an MD simulation based on a simplified tight binding model, so it captures some of the solid state physics effects, and maybe that's a way to look into this question.
Oh yeah, maybe. Yeah, because you can change the electron temperature in it. Yeah. Okay. Oh.
I'm wondering, how are you inferring the time-dependent electron temperature?
I am doing
Because that's not measured, right?
no, I do that by solving this set of equations, right?
Okay.
And so I know the ion temperature versus time, and is that how I do it? No, I don't use these set of equations. Essentially, I know the heat capacity of the electrons, I know the heat capacity of the ions, which I take from models, and I know the ion temperature, and then I do conservation of energy between the two subsystems, and you can work out the electron temperature.
So the one thing that I noticed is that in all the cases, and maybe this is why, the electron temperature seems to have the same time history as opposed to the ion temperature as a function of fluence.
No. This one, I mean, this one here, it starts.
I mean, the shapes look the same, I guess.
The shapes look the same, but this
Yeah.
one is much higher, right? So this one here, right? It starts at 10 eV.
Yeah.
And this one, the electrons start at 3 eV.
Yeah, I guess if you look at dt for those, it looks like they're all the same shape as opposed to the ion.
Oh,
dt.
okay, I see what you're asking. I see what you're
The
asking.
depositions.
When I did this,
Yeah.
we ignore this.
Okay.
I'm ignoring it because I don't know what's going on. So when I fit, I essentially just take like these points here in order to be able to calculate that. Yeah.
I won't hog anymore. So.
Mine from Minta Egin. How would this extend to a compound or eutectic, etc. mixtures?
That's a great question. I don't know. My guess is that my guess is that in this spectrum, this broadened spectrum, you'll see, right? You'll see from this equation in the bottom right that the broadening is related to the ion temperature, but also the mass of the atom or the ion. And so if you were to have a compound like CH, even something simple like that, then you're going to get two spectra superimposed up on each other, and each will scatter proportional to the z² roughly of the ion. So you'll get more from the carbon, for example, but they're going to be superimposed. I think it's going to be a nightmare. I think I wouldn't do it. I wouldn't try to do it. If one day if we can run at 100 hertz or 1,000 hertz, and we can really do this at high rep rate, then we may be able to get the resolution to see these spectra and be able to deconvolve the two Gaussians on top of each other, and maybe even look at interspecies equilibration and things like that. But right now, I just get this blob and I look at its width, and that's about the limit of the technology that we have. Yeah.
Thanks. For the fluences you had, is the X-ray laser doing the heating, or do you have a secondary laser shooting
No,
on
the
it?
X-ray laser does not heat anything up at all.
Okay.
One of the main reasons, so the X-ray laser is pretty powerful. It can heat, and people have done experiments where they heat with it. But once you've passed it through this monochromator, there's nothing coming out the other side. I mean, that's the problem with the experiment. And so we don't do any heating with the X-rays themselves.
So the wavelength is from a frequency doubled.
Yeah, we have a 400 nanometer
okay.
TAF laser pumping this experiment.
Okay.
Okay.
So it's my comment is actually connected to the X-ray heating. I mean, there is a new beamline being developed where you have soft and hard X-rays.
Yep.
And it would be wonderful, I mean, to have the X-ray heating.
You know what? It's 100% true. So you use this is the question, right? There's a new beamline where you can have soft and hard X-rays, and you can delay them with respect to each other. So you could design a wonderful experiment where you pump it with the X-rays and you measure the temperature with the X-rays, and you've got perfect correlation between them. It sounds like the perfect experiment, but of course, what you don't think about is the monochromator. So the monochromator can only let through one X-ray energy. So if you had two pulses coming one after another, the soft would not get through, and then the hard would get through, for example. So you would have to like chicane off some of the X-rays and send them around the monochromator to do the heating. I think it could be done, but but it's not the trivial experiment that I thought it was. When I heard that, I thought, oh my gosh, this is going to be great, because with an X-ray you can heat a big chunk of material and really improve the photometrics of this particular experiment. Yeah.
In the room or online? Yeah.
Thanks. So the in the time varying diffraction plot that you had, the diffraction intensity goes down first time, but you said you can't see the liquid. So I'm thinking about, like, you've got an 8 EV electron that comes in, it hits an ion. How do you know you don't have partial melting that's continuously happening rather than a discrete event once you've paid off the latent heat?
Yeah, that's a good question. So you could also, so there's two ways in which the Bragg peak intensity can go down. You can heat it all up uniformly, and you can also have like a melt front coming in from the outside in, changing the volume fraction of solid and liquid, right? And so here we heat this up so drastically, we are very much in what's called the homogeneous nucleation regime. So it's all going to go at once rather than having a melt front come in. Is that your question?
Kind of. I mean, I guess I'm thinking from a kinetic perspective. If there's an 8 EV electron that hits an ion, it's just going to eject it from its lattice site.
An ATV
electron. Yeah, if the electrons are hot and the ions are cold. So like how
I don't think it's going to eject an ion from its lattice site.
Because it's bound more deeply than that.
Yeah, I mean, yeah, the thermal electrons, which can be at ATV, well, ATV temperature, which means there's plenty way hotter, like way more energetic than that.
Sure.
Yeah, they don't move the ions really. I mean, there's some collisions and the ions warm up, but they're not knocking them out of the lattice sites.
Okay. All right, thanks.
Any other questions? Let me just real quick check that there are no questions online. So if there are no other questions in the room, let's thank Thomas again for the very nice talk.
Thank you very much.
Thank you everyone for engaging in this long discussion, and thank you for coming. Hope to see you next time.
Thank you.